That's regular computer program. It could be like the program is adding 2 numbers and my data is numbers like 2 and 3 and the output becomes 5. Examples are like apps, websites, and it could be like, console applications and things of that nature. The difference from any of these programs to a machine learning activity is we don't have programs in machine learning. We have an idea of what the program is supposed to do. The whole process is about creating the program from a given set of input data and a given set of equivalent output data. For each of these input data which is given, a respective output data is given, and we want the computer to figure out how the program should be. And that's all about is machine learning. Now, types of machine learning, again, I'm sure these are very preliminary material you have seen. There are supervised learning, unsupervised learning, and reinforcement learning. And content today, and in the supervised learning, it's very well structured and a guided activity. Feedback is available for correction at each step. Objectives are very well defined. And once the criteria is met, the learning stops. Mostly used for classification and regression tasks, and that is where the decision trees fall under the category, and I will be talking about this. Now, decision tree is one of the mechanisms of supervised learning. There are others. Now, let's try to spend a minute or two to find out what's the difference between a classification and a regression. Now, suppose, let's say I have some statistics or some data points of an observation. For example, there is a student who has come in. I have data points like the height, the weight, the hair length, and what kind of dress the person was wearing and things of that nature. And I want to do a classification activity, which basically means that I want to find out or categorize this particular student who has come into a male student or a female student. Now here what is happening is that we have a finite set of outcomes which are available to us. Now when we try to take some observation and try to bucketize into one of the categories which are very small in number, typically small in number. Of course, it could run to thousands, but typically small in number, and are a well-defined set of bucketizations or buckets which are available. That process is called classification. How is it different from regression? The regression is also like a classification task. Only thing is that the outcome is more or less continuous, okay? And you can have infinite outcomes. Suppose we make the classification task like boys as 0 and girls as 1, then you can't have an output which can be like 0.7, 0.8. It has to be, for the final outcome, it has to be either 0 or 1. It can't be anywhere in between. Whereas in a regression task, I can have any number of values between 0 and 1. And we can have, so outcomes are more or less infinite, and that's where we try to distinguish between regression and classification. Of course, there are other definitions for it, but this is one of the simplest and most relatable one is where I try to come up with. Now, before we get into the decision tree, it's important for us to kind of take a look at the different data types which are available. Now, like in the earlier slide, I have already said, we have past data, we have what are the outputs or outcomes which are available or what should be for this past data, and we feed in, we generate a model. That's basically my model, and model is nothing but a set of data points and a set of rules. Okay, and using these data points and the rules, I would be able to take any future new data and be able to generate an answer. That's how the machine learning. The top portion is more of where the learning happens, and the bottom portion is where we use the learned model into our production activities. Now, if we look at the different kind of data which gets used for such kind of model building, or subsequently for usage of the model to generate an output, we have data which are nominal. For example, names, phone numbers, IDs. Okay, even though the phone numbers are numeric, but the number doesn't mean anything. You can't take two persons' phone number and say that, okay, it means something else. Okay, they are meaningless things. They are like someone's name only. Only thing is that the representation is in terms of numbers. You can't say one phone number is greater than other or smaller than other. Or you can say that my number is a higher number than yours, hence it means something. That don't mean anything. These are nominal kind of data points. Ordinal is you may have things, but then there is an order. For example, good, bad, ugly, or high, medium, low, or the different grades which are given out in the exams, like A, B, C kind of grading. Or you can have a 2-star, 3-star, 5-star rating, which is there. These kind of things are ordinal values. Again, you can add them up to mean something, but there is a relationship or ordering in these ranks. For example, A grade is supposed to be a better grade than that of B grade, which is a better grade than that of a C grade, which is better than fail grade. Okay. Now, when we are saying that a is good student versus an average student, okay, then there is a ranking system by which it is there. So there is the greater than, lesser than sign, which basically makes some meaning in there. But you may not be able to add up these grades to say that A grade plus B grade means something. That doesn't mean anything. Okay. When it comes to intervals, these are more like integer values. Now they could be continuous integers or could be a discrete set of integers which are there. For example, let's say years or dates, or sometimes we say the age of something in terms of hundreds of years. Okay, or sometimes in millions of years or billions of years. Okay, we try to place like the stars distance in terms of billions of years. Those are basically interval kind of data points. And ratio is the rest, where you have continuous values, real numbers like height, weight, BMI. Okay, all these kind of things. Now, using this data, we try to come up with a classification. Now, let's look at how things are working out, right? Now, for example, let's say a decision tree is that which helps us to classify and arrive at a decision, while a regression tree helps us to predict or estimate a value. For example, look at this data set or the observation, which is the profession is equal to, that is basically it's a student as a profession, the field of study is science, and the income is high. Then we want to find out whether such an individual is likely to buy a computer in terms of either yes or no. Okay, and we say that the decision is buying a computer, yes. Then that's basically a classification we are trying to arrive at, depending on these attributes like what is the profession, what is the field of study, and what is the income group. All right. Whereas there are other situations, for example, I want to go for an exchange of an old mobile to buy a new mobile. Or it could be like, I want to sell my old car. I want to find what is the value. Okay. For example, the model is Moto Z5 Plus and age is 5+ years. I've been using a phone for 5+ years and the model is Moto Z5 Plus and the usage condition is good. And whether the working condition, yeah, if working condition is working, I basically give this kind of inputs to a system and the system generates an exchange value for me, being, let's say something like 2,700 rupees is the value of the phone for me. Okay. So that kind of condition, now it could be 2,700, it could be 2,701, or it could be 2,701.5, something of that nature can come in. But I think you get an idea of the difference between how a decision tree can be used for either a classification task or for a regression task. That being said, let's look at some decision tree, how it happens. For example, here I have taken a sample data set where we have the attributes like age, and the age has been, age is a continuous variable. I could have age of 1, 2, 3, 4 going up to 70, 80, 85, 100, 102, whatever. Okay. But for the sake of our classification, we try to put them into different buckets. And that's where we try to convert a quantitative data to a categorical data. Okay. And in this case, as you can see, we have tried to bucketize it into less than 30 years, 30 to 40 years, and greater than 40 years, making it more like an ordinal pair or ordinal set of values or ordinal set of age groups. We can say that less than 30 is young population, middle aged, and senior people. Okay, so that kind of grouping which has been done. Now this is how the age attribute is and the values are. Now income could again be categorized into, while the income value not necessarily of the person, it could be of the person of the parents or something of that nature. While the value of the income is a real number, for example, how much money I am earning in a year is a continuous value. Okay. But then again, for the sake of our understanding and classification, we are trying to say that, okay, we are not interested in exactly how much money you are earning, but we want to know whether you fall into the bucket of low income group, medium income group, or high income group. Okay. So that's the second attribute. And the third attribute is whether you are a student or not a student. Then credit rating, how much credit rating you already have. Now that we can pull out from something. Again, credit rating is a continuous number which is available if you try to take it from the credit rating agency. But again, for the sake of our purpose of analysis, we try to say that whether a credit rating is fair, which means it is less than 700, or it is excellent, which means it is above 700. All right. Then basically we want to use this kind of attributes which are available for an individual to decide whether the person is likely to buy a computer or not. And thereby we can create our marketing material and things of that nature and try to sell more computers. So when we have, let's say, the first node in a decision tree at this point of time is the age. Okay. So we said that whether the age is less than 30 years, 30 to 40 years, or greater than 40 years. And we said that, okay, here is an individual who just come in and the individual is less than 30 years. Then the next question which we try to ask is that, is this a student or not a student? Then because if it is less than 30 years and a student, this is likely to buy a computer, then the answer is yes. If it is not a student, then it is likely that the person will not buy a computer. So we try to create or construct different nodes and then go and split these nodes to create branches, and finally we arrive at an answer or a classification value, what we desire to get in. Now, how do we do that? Let's look at how a tree, what are the different nomenclatures we use for a decision tree. For example, at the top, what is the first attribute we try to do for doing a categorization of the data into different groups? That is called root node. Like in the earlier previous slide, we had this age is the root node. Okay, we used age is the first attribute basis which we are trying to do. Like division, split. That is why that is called a root node. It's like a tree. It starts with the root and grows upwards. Branches, trunk and branches, they split out, right? All the other nodes, but the splitting is happening in between. Okay, they are called as intermediate nodes. Okay. Now, we have the predicate logic at each of the nodes where the splitting happens. And once the splitting logic is basically employed, we have a set of outcomes coming out of the split. So different branches will come out, and each branch is an outcome of this logic of splitting which is employed. These are outcomes which are there for a decision tree, for a split logic at a node. Now, these outcomes are there for the root node as well as for all the intermediate nodes. Finally, when we have a decision clearly given out, okay, and at the end of the tree, just like as you go and start tracing a tree from the root, go to the trunk to branch and keep on reaching, where is the tip of this? That's basically a leaf. So those are the terminal nodes, or also called as leaf nodes, okay, related to the tree, as we see. The leaf nodes are basically the decision makers. They will give us a decision. Yes, no decision in a computer buying. Okay, likely to defer, not deferred in case of a loan grant to be given, or it could be like, whether the person is a boy or girl, if we are trying to do a gender discrimination or things of that nature. All right, so we call them, this is basically the anatomy of a tree. Now let's move on to see a geometrical view. For example, here is a layout of the data, scatter plot of the data which has been made. So this is some attribute on the x-axis and some other attribute on the y-axis. And we have these, let's say, these red circles. And there are these, which are minus signs. And we have these blue circles, which are the plus signs. All right. Now we want to come up with a structure by which we can do a distinction between the red circles to the blue circles. Oh, sorry, blue circles, which is the minus and positive plus classes, positive and negative classes. So we could start with saying that, okay, we look at this y-axis and we try to do a split along the y-axis at a value which is greater than 1 but less than 2. Okay. So let's say 0.5. Is it less than, 1.5? If it is less than 1.5, then it becomes to a leaf node, which is the negative classes. If it is greater than 1.5, then it goes to another node, which is yet not able to decide whether it is a positive class or a negative class. Okay. Then on that, we can try to say that, okay, if it is greater than 1.5, is it like, on the x-axis, is it less than 1.5 or greater than 1.5? So we said that, okay, if it is less than 1.5, then it is a positive class. If it is greater than 1.5, we really don't know what is happening there. Then at the next node, we try to define whether the x is greater than 3.5 or is it less than 3.5. If it is greater than 3.5, then it becomes a positive class. If it is less than 3.5, then we don't know, because we have less than 3.5 positive classes as well as negative classes. And at that point of time, we provide a Y logic to say that whether it is Y logic of greater than 3.5 or less than 3.5, this is which we'll be able to distinguish. So there are these splits which are happening at each of the points where we have indecisiveness till the time each of the leaf nodes are attended, and we only have a very clear answer whether it is a yes or a no, or whether it is a positive class or a negative class. We go on doing this. Now, here, while it is a horizontal vertical split, necessarily it doesn't have to follow that structure. Sometimes it could follow a combination of X and Y. Like, we can create straight lines in the Euclidean space and then try to divide the space into things. The core point is that in a vector space where we have all these data points which are present, we successively go on dividing this space using planes or hyperplanes. Okay. And till the time we arrive at very clear distinction in terms of the class values of each one of these things. That's how a decision tree gets built. Now, let's try to put a formal definition about this decision tree. Now, a decision tree is a tree in which each branch or node represents a choice which is between a number of alternatives, and each leaf node represents a decision. Like I said, that at the leaf node, you don't have any ambiguities. You are in a position to say whether it is a boy or girl, whether it is a man or woman, whether it is a good student, not good student, whether the student should pass or fail, or whether the person is likely to buy a computer or not, or to a bank, whether the bank should give a loan. The decision is very clear. There is no ambiguity at a leaf. That's how a decision tree gets built. Okay, and it's of course a supervised learning paradigm which is there. Now, given a data set, okay, which D consisting of T1 to Tn set of tuples, okay, data tuples, and each of these data in the data tuple which we have a set of features. Like any Ti, if we pick it up, it will have a set of features F1 to Fn. Okay, so it's a vector. It could be a vector. Actually, it could be a vector, or it could be a matrix. Okay, 2-dimensional, 3-dimensional. It could create a tensor. Doesn't matter. But it's a set of data points, set of features which are organized in a logical order to arrive at a data point. Now, these are our observations. The T1, T2, Tn, the data tuples are our observations of a physical entity which is there. We try to measure this physical entity, observe this physical entity, arrive at these features or attributes, and then we describe that particular entity which is there, physical entity, with a set of attributes. For example, a student into an entity might have an enrollment number, might have a class to which the student belongs, maybe a section, whether the student is a male or female, the student's demography, for example, whether the student is from Odisha or from outside Odisha, from India, outside India, and those kind of things. The student is a physical entity. Okay. Things such as what is the enrollment number, which year is the admission, which class and section the student is enrolled into, are the features or the attributes to describe that student. Okay. Now we are trying to take these descriptors of that particular physical entity, and we are trying to find out whether the student is a male or female, or is a pass or fail, or should buy a computer, or is likely to buy a computer, not buy a computer. That's where our set of classes come in, which are C1 to Ck. Now, using these kind of data points which are available with us, okay, a decision tree is a tree associated with D, okay, or maps D, okay. Decision tree basically is a decision tree is the set of data points, and C is the set of observations. We are trying to relate the data points to the different observations and create that tree. Like in the first slide, I said that you have a set of data, you have a set of observations. You are trying to create a model or a program. As you will be able to take any future data point like Ti or Tk or Tj which will come in and be able to assign a class value Cj to it. Okay. The edges are the predicates which are applied to the attribute node, and each leaf node is labeled as a class Cj because at leaf node we have very clear decision of what the decision should be. We have very clear view of what the decision should be. There is no ambiguity about it at that point of time. But there are some questions. Okay. For example, given a set of attributes which are available to me, what should be the rule? How do we choose an attribute at any point? Okay. Now, to start with, I have like 4 or 5 different attributes which are available with me. What is the age group? What is the income group? Whether it is a student or not? What is the credit rating? These are the different attributes which are available to me. Now, how do I start with choosing what should be the right attribute to be taken in the first for doing the space partition? Like in the earlier plus or minus sign, whether I should take the y-axis as my first attribute, some value, or should I take x-axis as my kind of splitting axis? How do I choose that? That is important. Okay. Now, there are certain ways to do it. For example, if we look at it, like the same data set which I was showing some time back, all right? Now, let's say the outcome, right? We don't know which attribute to be taken, but we are interested in finding people who buy computer versus people who don't buy computer. Now, if you look at this, what is happening is that the set of outcomes which we are observing here, okay? If you look at it, buys computer, yes, of the 14 data points which are available here, buys computer, yes, is it 9 of them are present, and no, 5 of them are present. That means it is not that everyone who we are trying to profile buys a computer. There is, if someone asks a question, given any person, what is the likelihood that the person is going to buy a computer? You can't for sure say that the person is going to buy a computer or not going to buy a computer. There is little indecisiveness around it. Okay. And this indecisiveness leads to defining how our impurities get measured. That means indecisiveness is related to what is called impurity in decision terminology. Okay. And how we create the metric around this impurity, measure these impurities and take decision is what we are going to discuss now. For example, if we are taking, let's say, student as our first attribute, let's say for randomly, we are trying to take a dart and throw it in the darkness. It goes and hits on the attribute called student. Now we said, okay, let's take student as the first attribute and see how it is going to divide. Now, when we take the student, we have 2 different values of student, either yes or no. And we are trying to say that, okay, taking that student as the attribute, we try to split it with yes as one group and no as one group and see what is happening to buying of computers. Now, if we say if student is yes, then how many yes students are there? Student is yes is 1, 2, 3, 4, 5, 6, and 7. 7 students are there, which are 7 people out of this 14 are there who are students, and 7 are there who are not students. Now, if student is yes category, then the buys computer no is 1, buys computer yes is 6. So it is not a very clear decision as we can arrive at, right? Even if I say student is yes, can I decisively say the student buys a computer? The answer is no. Because I have both possibilities coming with student is yes. Now, when student is no, again, both possibilities are there. Some of the students know there are people who are not students, they buy computer. There are people who are not students and they don't buy computer. So again, there is a little bit of ambiguity with student classification going to yes or no at the next level to see whether we should be able to say whether it is able to, we can say whether someone buys a computer or not. Okay, then we say that, okay, that's fine. If we try to split it with student, this is how the splitting happens, and this is how the outcomes ambiguity is there at the next level. What about if we take credit rating as our node, okay, or the attribute on which we try to do a split. Now, again, you can see credit rating has 2 different values. One is excellent, other is fair. And if you can see in the credit rating, Excellent. We have 1, 2, 3, 4, 5, and 6. All right. Now 6 of them are there. Okay. Now, so what we will do is that, okay, if the credit rating is excellent, is it that once you have a credit rating excellent, everyone buys a computer? And if you try to look at this node, what is happening is that credit rating is excellent. There are 6 individuals which we are able to find, and the buys a computer or not buys a computer is equally split. That means there is a huge ambiguity whether we can say if credit rating is excellent, someone buys a computer. What about if the credit rating is fair? If it is fair, are we able to decide? If it is fair, if we go into that node, we see that buys computer, yes, buys computer, no. Even though there is not an equal split, but there is a split. There is ambiguity which is sitting here. So we will not be able to say for sure whether the credit rating is excellent or fair leads to a decision whether someone buys computer or not. Now it's a confusion for me, right? How do I decide? How to decide which attribute to choose at this node then? Similarly, if we go for each one of these things, we may have a problem. We may not be able to decide for sure. If I do a split, I will be able to decide whether someone buys a computer or not. Now, given that situation, how to choose what is the right attribute to be taken at this first node? Okay, what are the different impurity metrics which can be employed? The measures which can be employed, this is which we will be able to take a more sensible decision. This brings us to a measure called entropy. All of you have heard of this term entropy. We don't have to talk of engineering. We don't have to talk of graduation. Entropy is a term we have studied either in high school chemistry, or if not in high school chemistry, then at least in PU or +2 chemistry. What is entropy? Entropy is randomness. Okay, when we are studying the properties of gas, okay, we studied about entropy. And we also know that entropy goes on increasing in the world and things of that nature, right? Now let's bring it back. Let's keep that concept in mind. What is entropy? Entropy is randomness. Okay, what is randomness? Randomness is basically you don't have something about which you can predict something for the future. Our inability to predict something into the future is randomness, okay, or uncertainty, and that's how gets represented by entropy. Into the engineering science when we come in, okay, into our data science when we come in, it is also associated. There are certain things which are associated with entropy because there is a randomness, just like we observed in ambiguity in our previous example. We want to find out whether an individual is able to decide whether to buy a computer or not. And because we have that ambiguity, we don't know how to decide. There is randomness. And because of that randomness, we can bring in the concept of entropy. And the concept of entropy mathematically gets represented as the probability of an event outcome into the log probability of the event outcome. Okay? And that basically says the sum of all the different outcomes which are possible for an event is what we take in and represent as an entropy. Now, that's too much of a complex thing, right? Let's look at it a little graphically so that we can relate to it better. For example, let's say you have a set of outcomes which are like only blue dots like this. Is there any ambiguity here? No. Okay. If I go and let's say there is a bucket, the bucket contains only blue balls. Okay. This like construction level balls are there. Okay. And you are trying to say that, okay, if I put my hand by closing my eyes into this bucket and I am going to pull out a ball, what's the likely color of the ball? Now, obviously it is blue because every color, every ball which is present in this bucket is in blue in color. Okay, there is no ambiguity there. Now, what if there is a little bit of ambiguity introduced into this by saying that, okay, while most of the color balls which are present in this bucket or in this bin or into the bag, okay, are blue, but there are few balls which are yellow in color. Now, would you be able to say, if I put closing my eyes, I put my hand into the bag and try to pull out a ball, is it going to be blue color? then you will say that, okay, it is most likely to be a blue color because majority of the balls present there is blue. Okay. However, since a few yellow color balls are there and you are doing just a random sampling, you are just trying to put your hand and probably steer it a little bit and then pull out a ball, then yeah, for sure I can't say that it is going to be a blue ball. It is most likely to be a blue ball. So here you can see in this case, in this C case, where everything was a blue ball, you had no randomness, no ambiguity, and hence the entropy is 0. Decisively everything is coming out as blue ball. There is no ambiguity. Okay, I put my hand, even when I am sleeping, you take my hand and put it into the particular bucket or into the bag, I will pull out something that is like to be a blue ball. Okay, there is no ambiguity there. Entropy is 0. When we look at this bucket where some of the balls are blue, then you can say that, okay, I am not sure anymore. Right? There is ambiguity there. And because there is ambiguity, while I can say with a confidence that it is likely to be a blue ball, but I can't be absolutely, I can guarantee you that it is going to be a blue ball. There can be a blue ball coming out. Now, as you can see, the ambiguity, while has not become fully random, has increased a little bit. Earlier, your ambiguity was 0. Now it has increased. You are saying that, okay, it is likely that 80% of the balls are blue in color and 20% are yellow in color. I can be very confident, up to 80% confident that the ball is going to be blue, but I am still having little indecisiveness around that. Now, as you can see, if we are trying to pull out that a ball and the event is basically pulling out the ball and the outcome is basically whether it is blue or yellow, then there is a probability of blue balls associated, there is a probability of yellow balls being pulled out, and because of this probability, there is a little bit of ambiguity which is coming in, and that is leading to my evaluation of entropy here. Now let's imagine this situation where blue balls and yellow balls are equally distributed. Now you are not sure anymore. You don't have any confidence in it. Okay. If I say that, okay, I put my hand into this bag and pull out a ball. Now tell me whether it is likely to be a blue or yellow. Then it's that, okay, I have no clue. Okay. Because it is equally likely to be yellow or blue. Now my ambiguity is at its highest. Okay. And that is the point where my entropy also becomes high. All right. Now the color changes doesn't matter anything. The entropy goes in decreasing. So if you look at it, try to make a plot of the entropy. The entropy, when you have, let's say, color yellow 0, okay, color blue is 0. Entropy is color blue. You have absolute like an assertiveness in terms of the ball being blue. Entropy is 0. As it goes on increasing, you go on adding more yellow and yellow balls. At some point of time, the number of yellow balls and blue balls is same. The entropy is highest here. And you go on increasing yellow balls further, then the entropy decreases because now your assurance or your confidence of pulling out something yellow goes on increasing. And then finally, when there are no more blue balls, everything is replaced with only yellow balls. You have no entropy anymore because you for sure know that whatever I'm going to pull out, there is no blue ball. Okay, everything is there. Okay, that's how it changes. Now let's calculate. Okay. For example, let's do a quick exercise in terms of calculating entropy. Let's say I'm trying to toss a coin. Now, when I toss a coin, the outcome is going to be a head or is going to be a tail. Now, let's say I do this toss 10 times. So my event is tossing a coin. Outcome is it could be a head or it could be a tail. Now, suppose the count of events is 10. That means basically I tossed it 10 times. And all of them turned out to be head. Some sheer coincidence. Okay. Because of that, everything turned out to be head. Now, what becomes my probability? The probability of head becomes 1. Probability of tails becomes 0. Okay. How do we calculate entropy? I will take probability of head into log of probability of head plus probability of tail into log probability of tail. And then I'll multiply the log with the probability and add them on. And apply a negative sign. I'll apply a negative sign because otherwise, since the probabilities are less than 0, the entropy, the log probabilities will become negative. I just want to see something in a positive sense. So I just apply negative sign in the beginning, right? Now, if probability of head is 1, then the log probability of 1, log probability of head becomes 0. Log of 1 is 0. So the first term becomes 0. 0 multiplied with 1 becomes 0. Now the second term anyway becomes 0 because the probability is 0. I don't have to go to the log value. Okay. So effectively what happens is that here it is 0. The second term becomes 0. The finally entropy becomes 0. And you can relate that because entropy is 0 and everything is head. That means there is no randomness, no ambiguity. And that basically calculates to 0. That's all it is. What if, let's say, I toss it 10 times and 2 tails come out and 8 heads come out? How does the entropy look like? Now the entropy will become probability of head becomes 8.8 and probability of tail becomes 0.2. Now you could do the calculation. It is 0.8 into log of 0.8 plus 0.2 into log of 0.2. So it will become some number which is like 0.7. Now let's look at the worst scenario. The worst scenario is equal number of heads and tails, which is likely to happen. Okay. Now my probability becomes 0.5 and 0.5, and that's what the log probability and probability multiplication add for each of the outcomes which can happen when in my experiment the entropy is the highest and it becomes 1. Okay. So just like as we were seeing in the previous graph, it started with 0, it went and become somewhere like 0.71 and then it becomes 1 at the most random scenario. And after that it will start falling because then the probabilities of head and tail will start reversing and then it will start going down till the time everything becomes tail, it will again become 0. So now from this, let's try to see how do we measure, right? And that's where comes information gain. Information gain is a measure where we say that, okay, before the set is split, what was my entropy? Okay. And after the set is split into different sets, then each of those outcome sets will also have some entropy. Now I want to find out if there is a change in entropy which has come in because of the splitting which has happened. Okay. Now the initial set is S, like I had these 14 people with outcomes Bayes computer, not Bayes computer. Now if my event is basically, I want to determine whether someone buys a computer, just like head and tail. Someone buys a computer, not buys a computer. The entropy associated is probability of Bayes computer equal to yes, the probability of Bayes computer equal to, that will lead to generation of the entropy at the initial set for all the 14 people. Then I said that, okay, I do a set division by student, whether the student is yes or no. Then my SV basically is 2 partitions I'm generating. All right. I have one partition with student equal to yes, the other partition with student equal to no. And for each of those partitions, I'll have some entropy, as we saw in the previous slide. If student is yes, Bayes computer is equal to yes is 6, Bayes computer no equal to 1, and this will lead to generation of some entropy. And if student is equal to no, then it will also lead to some entropy. I do a weighted averaging of these entropies of each of the split cells, okay, and then see whether my entropy has reduced or it has remained same or it has increased. Can it ever increase? The answer is no. Okay. The sum total of the weighted average, sum of all these entropies will actually increase only in a scenario where you are adding more randomness into this set by splitting it. That's not possible. The worst scenario which can happen is that you have a set, okay, of student buying, not buying, students yes, student yes, student no, person buying, person not buying. Now on the set splitting, it is done in such a manner that there are these yes group of students, there are these no group of students, and buying computer, not buying computer is equiprobable to the initial set. Only in that scenario, the entropy remains same and my gain becomes 0. In all other scenario, the randomness goes on reducing and thereby the gain is there in terms of my certainty, right? So it is going to be a positive value. With this, now let's look at do a information gain calculation. For example, this thing where we are saying that, okay, we have taken student is equal to yes. Okay, now the student is my attribute. Okay, So my S is having initial entropy of 9 and 5, and that is having 0.9 for entropy. Now S1 is basically student is equal to S. Yes, student is yes is my S1 set. That also has entropy because here buying computer, yes is 6 and no is equal to 1. I use that, I get 0.59. Then I have the second set, which is S2. That is where I have the buying computer 3, not buying computer 4. There is an entropy associated with it. It is having 0.98. As you can see here, buying computer yes is highly dominant than buying computer no. There is a high level of certainty or confidence. You can say that if the person is a student, then it is more likely to buy a computer. And you can see that the entropy is low here. Okay. Like the student is known, then the buying computer yes and no is equally, almost equally split. If not fully equally, but it is almost equally split. And because of this equality in terms of split, you have higher ambiguity, and thereby the entropy is also high, which is very close to 1.9. Now, what is my information gain? Information gain is I'm going to use what is my original center entropy, which is 0.94, and the weighing of the things with respect to the partition which has happened. In this case, 0.5, because 7 are yes and 7 are no. So 0.5 times the entropy associated with buying yes, which is 0.59, and 0.5 times with student equal to no, buying computer 0.98. So 0.5 into 98. So when we take that weighing of the entropies and then add them up, it is coming to 0.78. I have a gain of 0.16. So if I take my node, root node, and the attribute is student, I have an information gain of 0.16 if I try to use the student as my attribute and do a split based on whether the person is a student or not. What if I try to do with credit rating, like the earlier example we did? So we said that, okay, if I do the same calculation for credit rating, I'm getting an information gain of 0.05, which means if I'm taking student as my attribute, I'm able to reduce the randomness to a greater degree than if I'm trying to take credit rating as my attribute and do a split. You can see the same thing here. There is a higher order of randomness in each one of the partition sets if I'm taking credit rating equal to fair or excellent. Then if I'm trying to take a student as yes or no, okay, and trying to do a split, you have a greater certainty in one of the sets here, and thereby leading to a higher information gain which is coming. Now, because the student is leading to a higher information gain, which otherwise means there is a higher reduction in uncertainty. So I should be selecting student as my first split. That's how I should do it. Okay. With that, I will just give me a minute, a quick time check. I'm almost closing on 1 year, so I'll move a little faster. Okay. So I take different attributes and see that the age is my criteria or attribute on which I get the highest information gain, and the income and student and other things, credit rating is low. So thereby I will take age my first rule. And when I try to construct a decision tree, it gets put down as rules like this. If age is less than 30 and the student is more, then Y is computer equal to no. If age is less than 30 and student is equal to yes, then Y is computer equal to yes. If age is between 30 and 40, Y is computer is yes. Okay, this is how my leaf nodes are getting constructed. And what are the other impurity measures? One is Gini index, where it is purely applying on like the probability of the outcome. Here we are not taking the log of the probability, we are only taking the square of the probability, adding them up, and then trying to find a difference from the original set, which is 1. All right, and see whether how it is. And each of these impurity measures, they have their advantages and disadvantages. I'll leave it for you to do some little self-study at a later point of time. Now the question is, when do we stop? What is that? First, let's understand what is depth of a tree. You start with a root node, then you go to the intermediate nodes till the time you reach the leaf nodes. Okay. How many splits we are making determines the depth of that tree. Okay, on any path. The path with maximum number of splits basically tells what is the depth of the tree. The longest path would reach the leaf node. The longest path in terms of how many splits it is going on is basically the depth. In this case, the depth is equal to 2 because one split happened here, other split happened here. Now, in this case, what has happened is that all the leaf nodes are attended with the 2 splits. Okay, so it's a uniform splitting happening here. Depth is 2 uniformly across all the paths. Now, this is three splits which is happening. As you can see, there are 3 layers. Before you reach a leaf node, you will have to take 3 decisions. So each of the leaf nodes can be described in terms of if condition 1 and condition 2 and condition 3. Each leaf node has to follow that. And that becomes depth of 3. Now here is an interesting scenario. All the leaf nodes are not at the same depth. Okay. Now you have the first classification of the first split, which is leading to a leaf node. Then you go the second set, which is created that has 2 more splits. Okay, and then from there on. But the longest path which is to be traced before we can reach the leaf node, or the leaf node with the longest path has number of splits 1, 2, 3, 4. So this is basically the 4 depth tree which we have. So that's basically from the root of the tree to the leaf. What is the longest distance which we have? That we try to measure and we try to see and find that is the depth. Now in this case it is depth, but in a tree, actual tree, physical tree, that is basically the height of the tree. So in this case, the height becomes the depth. Right? Now what happens? Is it good if we have a very long tree? If the depth is more equal? The answer is no. Why? It goes for overfitting of the data. Okay. Then what is underfitting? Now, if you try to overgeneralize, we just say that, okay, we take one of the attributes or maybe 2 attributes and we will construct a tree based on that. We might have some ambiguity, we'll live with it. But that becomes a very generalized. So for example, in our earlier case of student buys computer, there is a person buys computer. If we say that, okay, we'll generalize by saying that student yes buys computer, student no, not buys computer. Okay, that's a very overgeneralization we are trying to bring in. Okay, that will not give very good accuracy for our future data. Okay, we are likely to make more mistakes there. That's an underfitting we are talking about. Now, what is overfitting? If we go into very granular details, more complex scenarios, okay, the data could be described in very different. For example, here if you look at it, we are building like so many decision splits which we are doing because we want to accommodate each and every of the data points so that we attain 100% accuracy on our training set. That's a good thing to happen if the training set is actually representative of what is likely to happen in future. Okay, most frequent scenario that is not the case. Okay, so in real life, if we try to take the training set and build our decision tree so that it exactly fits to the training set, it is likely to take more mistakes because of overfitting. Okay, so very long trees, the trees with great depth are overfitting and hence should be avoided. How do we do that? For example, look at this thing. This is the image. I'll be using it for our demo, and you can see that this is the kind of depth which is coming. 14 depth. Okay, at different points, different kind of split happen. It is created such a messy tree, such a complex tree it has created. Okay. Now, these kind of things may lead to overfitting, depending on the. Sometimes it can go to a depth of 30. Sometimes it can go to a depth of 100. Okay. That becomes very complex, both in terms of computation. It will increase the computation. Cost of computation is high. The accuracy which it is likely to generate in future because of generalization being poor is also low. So it's a overfitting scenario. We should avoid that. How do we do that? We call something called as pruning. What do we mean by pruning? We don't go till the end step. Okay. So just like a tree has grown randomly in different directions, the branches have started coming out. Okay. That's a messy looking tree. We don't want such a tree in our country. What do? We take a scissor, we start trimming the branches so that it forms a nice tree structure for us. It looks good to us. And it's beautiful. Okay. Equivalent of that in our machine learning, what we try to do is that we prune the tree. The pruning can be done is that we try to stop the pruning at certain point by a predefined criteria so that the tree doesn't become messy. That is called pre-pruning. As the tree is growing, we are taking a decision and not going any further. That is pre-pruning. Post-pruning is that to construct the entire tree okay, to its full capacity, that is leading to 100% accuracy in its training set. Then we start cutting out some of the subtrees of the branches to make it look good. To make it look good equivalent here is that it starts giving better accuracy in terms of representation while having lower computational complexity. That kind of approach is called post-pruning. First, the tree is fully grown, then we start removing the branches from it so that we can prune it to make it more efficient. That is post-pruning. Now, what are regression trees? See, the same concept, what we talked till now about decision tree. Only thing is that the end value is not a class value. It's not a number, one number, which is very distinctly different from all other numbers, all other class values are there. Okay? But it is more of a continuous value down. Just like, let's say, my cell phone, I want to exchange, how like it. Or for example, I want to sell my old car or my old furniture. I want to sell it in the market, how much I am likely to get. Now we build a tree, okay? And finally, with reach the node, it may have multiple values, each of these values. So you can take an average of those values and say, okay, this is what is the likely value of your mobile phone or your car or your furniture or whatever else you can talk about. Okay? Or your potential to earn the salary, which can be happening. For example, whether you have taken computer science as a subject or you are from a non-computer science subject. Or your number of years of experience is like less than 10 years or more than 10 years. You belong to a group of people. And you can take the average of those group of people and their earning potential. You can say that, okay, I belong to that group and hence my earning potential is almost like the average of the group. So that's basically the more of groups, basically leaf groups we create here, the more number of potential to split the things coming. But essentially what can happen is that you are trying to arrive at a regression value. Now let's look at what is random forest. This is very interesting, right? It's an approach where we are saying that we are having a federated mechanism of decision making. It's not only one tree which is making that decision for you. That can go for underfitting, overfitting. We don't know upfront how it can happen. So what we could do is that we can say that, okay, given a set of data which is available to me. For example, let's say 1 million people's data is available to me or their earning potential. I can use this 1 million for constructing one tree. Alternately, I can divide this data set into multiple groups. Let's say I want to take 1 million, divide it into 20 groups, each of 50,000. And I want to create 50 decision trees. Now what will happen is that in future when a data point comes, I'll run it through each of these trees which are constructed. In each of these trees will make a decision for me. And going by a democratic approach, I'll say, I'll take the majority voting. Okay? Or if I want to do a regression, I can say that I'll take the average of the outcomes which have been generated by each of the trees. Okay? That's how I can do. So in the forest, like a forest is actually built with multiple trees. That's the same approach we follow here. We create multiple trees and try to arrive at a decision-making mechanism. Now here are the two ways we can do. We can say that, okay, we split the data set which is available to you for us to create multiple trees, in which case all these trees can run parallelly, and that is a mechanism of bagging. Okay? Then we will go by a voting mechanism to arrive at a decision. The alternative approach we can take is that instead of creating a partition into the observation set, we create partition into our attributes. We will take some attributes first and create a tree. From there, we will take the next set of attributes and create another tree. As you can see, here we are creating sequential structure. First, the observation goes to the first tree. It will create some outputs. And on that, we'll take it to the next set of attributes and employ. We'll say how the splitting is happening. Now, we can create a partially parallel, partially sequential structure. And that's like a boosting technique we are taking. Okay? But then what we are doing is that we are employing multiple trees, some of them in parallel, some of them in sequential manner working, arriving at a decision making. That is the process of random forest. Okay, this is like a parallel sequential. Now I'll go into the demos. Okay, before I get into demos, are there any questions? Okay. I don't know if So the participants can ask questions. If there are not,
any question from the participant side? I think there are no questions. If question will be asked from our side, then only you can know. They don't have any.
I think they can put it into the chat. Okay, I think request to the participants. You can post your questions in the chat window. I'll take it. Okay. All right. So I have
no question is there in the chat box also.
No problem. So I have created some small demo so that you can see to it. I have taken two sets of data. One is a go to college data set. Let me open this data set and show it to you so that you can relate to it better. Okay. So basically you have certain attributes here available, like type of school, school accreditation, gender, interest, residence, parentage, parent salary, house area, house grades, whether the parent was in college, then whether the student is likely to go to college, yes or no, this particular college, yes or no, right? Like that, this is the thing. Now we have around, as you can see here, up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 attributes, and the number of observations which is available is 1000. Okay, we'll try to create a tree and see what kind of accuracy it is given to us. Okay. So this is basically people who are already familiar with Python, and a course has already been given on Python. You just relate to it, importing libraries, then I am loading the data. Okay, and I can see that there are these different data and some of the different types which are available. For example, the strings are coming out as objects, and then we have integer and floating. Now, because I have non-integer values here for my tree construction, that is going to pose a challenge because computer deals with numbers here only. So what we need to do is that we will convert these objects, which are string variables like we saw here, whether the type of academic institution or vocational institution, accreditation or gender is male and female, accreditation thing, status is A, B kind of thing. We'll convert them into numbers by employing a technique called label encoding. Okay. Once the label encoding is done, so okay, this is done. Then let me do the label encoding. So once I do the label encoding, as you can see, before label encoding was done, the data were like academic, vocational, male, female, school accreditation, A, B, interested, very interested, less interested on certain residencies or one rural. All these things have been converted into numbers. Here it is academic, vocational, only two values are there. They have gone to 0 and 1. Whereas here, very less interested, very interested on certain, there are different values. So you can see that values are 0, 4, 3, 1, other things will also be there. Residence, urban, rural, then you have two values which are there. And then other things are like numeric values. So we'll not go into that. Gender is male, female. So you have 0 and 1. Accreditation A, B. So it is also 0 and 1. Like that, it has got label encoded. Once the label encoding is done, we also did, like, take the data set. We did a trend test split of the data. Out of the 1000 rows of data is there, I have split it into 20% testing and 80% training. That's the splitting which I have done. Now I will go and create or construct a tree. And as you can see, I'm calling this decision tree classifier. Okay. And that is getting imported from like, from sklearn.tree. I'm doing a decision tree classifier loading, which I have done. Okay. And I am calling that, and I'm putting my criterion is entropy. So here it is entropy calculation, not Gini index, which is there, but entropy based gain calculation, other things we will do, and it will try to do a best split based on the nodes at each of the levels. The nodes, whichever node gives the best entropy or information gain, it will take that as the splitting point. It's not going to do it randomly. And I'm saying that the max depth it should go to is 8. So I'm using a early pruning or pre-pruning criteria, saying that if the depth is likely to go beyond 8, but you stop at 8, you don't go beyond 8. Okay. Let me create these trees. Okay. As it has printed, it has constructed a tree, and the tree has gone up to 8 depth. And then I will try to see what is the score it generates for my training set and my test set. Let me run this. And as you can see, with the depth 8 for the training set, it has attained an accuracy of 94% in terms of its predicting the class values, whether a student is going to that school or not. Okay, going for school higher studies or not. Now, for the test score data which I created, please remember I took this 1000 rows and divided it randomly into 20% and 80% training and 20% training testing. On the test data, when I am running the tree, I'm getting 83% accuracy. Okay. Now let's plot the tree and see how it looks like. It takes a few seconds to plot the tree for us. Okay. As you can see, it has created a very nice tree and it has gone up to a depth of 8. And if you look at each of the nodes, okay, what it is basically doing is that each of the nodes it is putting some measures, right? What is the average grade and what is the entropy value which it has calculated. It goes to the next split. Similarly, it has put, and then it tells like how many likely to go, how many not likely to go. Those kind of decisioning it is creating. As you go through each of the nodes, you can see that it's basically giving the information about what will happen. This is how the tree got constructed. I employed always pulling, right? Now, what if, let's say, instead of using a depth of 8, let me put a depth of, let's say, randomly 5. Okay, what will happen? Let me reconstruct the tree with a depth of 5. Now it has created the tree. What kind of accuracy does it generate? Now you can see that the accuracy has, for the training set, has reduced to 90%. Test set has increased a little bit to 85%. Okay. Now, what if I don't put a max depth? I'll just close it here. Okay. I'm not defining the max depth. Let it grow till the time it is possible to grow the tree. Okay. It has gone up to 15 layers. Please remember this. Training accuracy is 90%. Test accuracy is 84%. Now let's run it on the fully grown tree. What is happening? You can see that the training accuracy is 100% and the test accuracy is 86%. Okay. So from a 5-level tree, okay, to a 15-level tree, how many depths and how much of extra computation it is doing? Okay. But from a generalization standpoint, when you are trying to put it, the increase in accuracy is minuscule. Okay, not much. So we can see that, okay, we may not go till 15 depth and we can probably cut it at 5 depth and see how that tree looks like. Now for our understanding, if I really want to see how that 15 depth tree looks like, let's see. And yeah, you can see that this is how the 15 depth tree looks like. Okay. And like earlier, I said that for each of them, you will see what the value is, how the splitting has happened, how many samples are there in each one of the splits and those kind of things. And just for a comparison, you can see how these two look like versus how the tree here is looking like. Okay. So we'll probably take it to the end and raise it. Okay. So this is how this tree looks like versus this is how this other tree looks like. Okay. You can get a comparative view. You can see that there are not every leaf node is arriving at 5 level or 8 level or whatever. There are some branches where it has gone to 15. There are others where the leaf node is much earlier available. Like this one, it has already ended here. There is no further thing. Okay. If you click this and try to see what is happening into that. For example, look at this. In some, like this probably second, third, third split, it has come. You can see that. Goes to college is 92, doesn't go to college. It has already reached an 80. Okay. But if you try to see the same thing here, okay. For example, if I want to do it, let's say max depth is 5, all right? Let's see how the leaf nodes look like. Okay. This is giving a better plot. So let me plot it this way. Okay. As you can see, we have all the leaf nodes here. But the leaf node, this leaf node is a pure leaf node. It's able to keep and generate, one class 52, other class 0. Whereas the next leaf node here still has ambiguity, 35, 6. Though it is biased towards 35, which is yes, highly likely to go to college. This is, but it's still. Whereas each one of the leaf nodes, if you start inspecting, each one of them may have their uncertainties. The split of uncertainty could vary and things of that nature. Some of them are clear, some of them are not. But some of the leaves are pure, some of them are having ambiguity and are impure. For example, here it is 20% versus 80%. Whereas here, if you look at it, this is like 10-26. So this is like 30% versus 70% kind of split which is happening. Okay. So this is how a tree gets constructed and all that. Now let's use the same data and try to build a random forest classifier. Okay. And when I constructed the random forest classifier, and again to a depth of 8, or let me put it for 5. Comparative analysis. While in generally the random forests are more stable, more likely to give higher accuracy. Okay. But there are times where that cannot happen. Okay. And the drawback of a random forest is basically because of multiple trees it creates, depending on how many trees it is creating, the computational complexity could be higher. Now, as you can see, in our 5 case here, we had, okay, max depth 5. Let me run the accuracy here. You can see. So 90% versus 84.5%. Training accuracy is 90.5% and test accuracy is 84.5%. Now, when we are doing it in the random forest, the training set accuracy has reduced a little bit from 90.5 to 90.4, and the test accuracy is improved a little bit, so from 84.5 to 85%. This is just a small indicator, right? So it is a better generalizer. Okay, more regular fit than the only tree which we had created. And again, for different layers or different levels of depth of tree, you can try to make a comparison. More or less, in regular fit scenario, you will get a better accuracy from random forest than that from an individual tree. So far we have looked at the decision tree and we have random forest. Now let's look at another experiment where we will see how the regression can be happening. Now for the regression, what I'm doing is that I'm using this data set called the California housing data set. We'll anyway see the data set, right? The value of the data set. So here what has happened is that the data set basically contains 1, 2, 3, 4, 5, 6, 7, 8, 9. And the 9th parameter is basically the value which we are having, the house value. So it's about the houses, price of the houses of a house you are trying to build, sell. What is the longitude, latitude, basically the location. What is the age of the house? That is another variable. How many total rooms are there? How many beds are there? Bedrooms are there? The population in that neighborhood, household and median income in the households and things of that nature are there. How many households are there? Population, total people and things of that nature is there around the house. This is that a particular house's value gets determined. So as you can see here, we have latitude, longitude information. It's from US. Okay, California housing. So the longitude is basically negative, which basically means on the western side. Latitude on the north hemisphere. Housing age 15 years, 20 years, like that, 14, 20 different age, and the median value of the houses are there. Okay. And the test data, again, I have done a trend test split of, I think, 20%. No, they basically have given trend and test. So I don't have to do a split here. So I have just loaded as they have given. So the test data is also similar to what we have in the training data. So let's go ahead and create a regression. So for the regressor, you have to call the decision tree regressor function. Okay. Earlier we called decision tree classifier. And I'm trying to put the tree here. Okay. This is a tree depth of 1. Okay. That means the first layer only they're making a decision. And with that, if you are doing, so here there is no accuracy, right? You are trying to predict a value. Now the value may match, may not match. In more frequent scenario, it may not match. Okay, there might be a slight variation. So here when we try to find out what is the similarity matrix, we don't try to take the match mismatch classification accuracy. We try to see what is the square error, what is expected value versus how much you have predicted and what's the error. Okay, we try to take the square error and try to add it up, which can get called as residual error or root mean square error or sum square error. You can have different values. So we try to say. Here we can say that, okay, the score value which we have used basically is the residual error. And we say that for the training data, we are getting a residual error of around 31. Accuracy is basically, so the score is 31% error. If we are doing a test data, actually the below is test data. So it should be called as test. Okay, then this is around 32%, very close by. What if I change this max depth from 1 to, let's say, 10? Okay, how the accuracy changes? The score in this case, how close proximity you can see. So here you can see the score has improved, the error has reduced. When I take it to a depth of 10, what is happening is that on the train data, the matching with the control data has increased to 84%, and the test data has increased to 74%. And I can go on doing that, right? So with that 10, I can go ahead and plot the figure to see how it will look like. Yeah. So I have taken only the predictive values of the median house value, right? We have the price. Median house value is the value at which the house can be sold or bought, right? Now that is the value against which we are trying to predict, and we are trying to see how the data looks like. Now obviously here what is happening is we have for the trend data and for the test data. If you see for the trend data, you can see that the trend data blue is what is the true value, and red is what is predicted. I think that is how I put it. Yeah, the prediction is red color, and the true value is the blue color. So if we see here, as you can see on this, you can see that the red value is more or less following the trend of the blue value, right? And for the training data at least. You can see how the training data change is happening. And okay, so if we move further, we can see that the red data, there are variations. There are places where it's not exactly matching it, but it is trying to match up to what is the true value. And how does it behave for, let's say, test data? This is basically for the test data, you can see. Again, here you can see that the red value is able to fairly match up to what is the blue value, and hence it was able to do a good job. Okay, so here we don't want to see the tree, we just wanted to see how the matching of the data values are coming up. Now let's see how the tree looks like. Now, this is a very complex thing, right? So we have created a tree here of depth 10. Now, because it's wide variability in terms of the median values, it will create a very complex tree. As you can see here, that is what it has done. Okay, but you can see that most of the leaves are at the level 10. Okay, they may not be very pure, but yet we have done an early stopping by employing it at a depth of 10, and then it is creating the tree and it is able to attempt this, right? Now, what if, let's say, I kind of remove this constraint of depth 10, okay? And let me put it something like 100. Does it actually go to 100 and beyond, or does it get clipped, or does it reach a termination condition before 100? Let's run this and see. As you can see, when I am giving the max depth of 100, okay, the tree got fully constructed with a depth of 35. Okay, that is basically the longest number of splits one is to go through to reach at the terminal node. Okay, with 35 depth, the tree got constructed. Now, in this case, you have to relate how the tree would actually do it. Now, for example, you have these different values of median house value, right? Now, because of these values, each of the values could be different from each other. So how many ever values are there, it will try to make it those many leaf nodes. It will do. Unless we are trying to say that the minimum number of members present in a leaf node is 3, 5, something. We can set it in our settings, right? So that means it will not go any further. But if we don't mention anything, then it will go and try to create as many leaf nodes as number of data points which are there, unless, let's say, there are 2 houses which are with 101 value. If there are 2 houses with 101 value and they follow the same kind of pattern, then those 2 will get clubbed and appear in one leaf node. But if, let's say, any of the values are different, okay, then what will happen is that it will create 2 leaf nodes. So it is most likely that if you don't specify any conditions, in a regression scenario, it is going to create a tree with a very large number of nodes. Okay. So here I think in the training set we have around 17,000 data points or something. So it is most likely that it will create a tree with 17,000 leaves. Okay. And that's a hugely complex tree. And the complexity of calculation going up to a depth of 35 is too much. Okay. So that's like you are trying to define so many if conditions with a AND condition of 35 different conditions which are there, and then you are trying to create a tree. And that's a huge computational complexity for us. But then with that, what happened is that in this case, the data exactly matches to what is there in the training data. And the test score, it has, as you can see, it has reduced quite a bit. Earlier, it was much better. I think we had around 84% matching with respect to the test data. Okay, and the training data was 94%. But here, as you can see, the trend data has gone to 100%, but the test data has drastically reduced. This is exactly a scenario what we were talking about is called as overfitting. The tree does a very fine job for your training data, but when it comes to test data, it is not able to generalize well. This is the situation of overfitting. Okay, and if we now, of course, if I try to create this tree in terms of this tree structure, I will be in a problematic scenario because it's probably going to run for, I don't know, yesterday when I was trying to run it, it was running for like 15-20 minutes without able to create it, because that hugely complex tree structure construction is going to take a lot of time. Let's not do that. But let's look at how the plots of the estimated values look like. That's something that you can do. So as you can see, there is no distinction between the blue line and the red line here. Okay. And let me do this also so that we can see these values. Okay. So here you can see this is for the training set and this is for the test set. In the training set, the red line is exactly following the pattern of the values as they are in the training set. But when it comes to test set, okay, you can see there is a much greater difference which is obtained by the tracing of the red line than that of the blue line. And that is leading to like what we created as higher error in the test set. Okay, this is how you can see and understand. And of course, like I was trying to do something, but due to lack of time, I couldn't do it. You can try to run the creation of that tree from, let's say, a depth of 1 going up to 2, 3, 4, 5, 7, 8, 9, 10, like that, up to 35. And for each of the depths, you can calculate what is the train error and what is the test error, and you can create a nice plot of it to see how the training and test variations are coming out, right? And then you can determine where is the regular fit, where is the overfit, where is the underfit, and you can determine what should be the depth at which you should stop it. Okay, or you can define other ways of criteria by which you can prune the tree and arrive at the values. With that, I think my time is up. I will stop my presentation here. If there are any questions, I'll be happy to take it. Otherwise, I'm good. Thank you. Over to you, Satyendra.
Thank you, sir. Thank you very much. Any question from the student side? Sir, few queries are there here in the chat box.
Let me open the chat box. Why the accuracy?
Yes. Satyajit is asking.
Okay. I'm saying starting with, let's say there is Sonal Panda, there is a question why the accuracy reduced. Like I explained, this is because of the overfitting. Okay. As the overfitting happens, what happens is the models fail to generalize. Okay, because the models are too focused on what is available to them. And now, related to the overfitting to a scenario, like for example, let's say a teacher is teaching you in the class. The teacher might be giving you examples, okay, in the class, so that you learn the concepts. The teacher is not giving examples to you so that you can actually reproduce them. Okay. Now, if you are too focused on what the teacher is saying and not trying to understand the concepts behind it, what will happen is that, let's say I give you an example of saying that add 2 numbers. Someone is trying to teach you add 2 numbers. And I'm giving you an example of take 2, take 3, add them up, it becomes 5. You are so focused on this example that you try to mug up 2 plus 3 is equal to 5 without understanding how addition happens. What will happen is then in the exam, when I ask you, saying that add 4 and 3, tell me what is the number. You will not be able to do it. You will probably arrive at some other number, right? Because you didn't try to generalize it in the learning. That's exactly what the machine learning happens. That's what we call as overfitting. Okay, you are too focused on what is being said. Then what is the concept which is being described here? That is where accuracy reduces. Okay. Now. For next session,
Satyajit having some questions, sir. Is it mandatory to normalize and standardize the data before the applying decision tree? Will it affect accuracy if you don't know?
Yeah.
Do this.
Yeah. Now, see, that basically goes into the data pre-processing stage, and a lot more things have to be taken into consideration. It is not only about normalize and standardize. Okay. There are different techniques. For example, you may have null values in the data. How do you handle that, right? One of the things which I handled here is level encoding, which is basically when you have categorical data and that to non-integer, non-numeric data, how do you handle that? Which is level encoding, you can go for one-hot encoding, things of that nature. Now, there could be dependency in the data, right? For example, let's say height in centimeter versus height in inches. Okay, they are highly correlated data. Now that and if they appear as 2 different attributes, you will have a problem. Okay. Now all these have to, ideally, when you are embarking on a project work, you should make sure that you have analyzed the data well, you have prepped the data well, which includes normalization. Now the normalization is also very tricky. For example, should you go for a Z-score normalization or should you go for a min-max scalar normalization? Okay. Now, that depends on how the distribution of the data is. Is it normally distributed or is it uniformly distributed? Or is it skewed towards kind of a chi-square kind of distribution? All right. It depends. There are different tricks which are to be applied, but that is to be learned and applied on a case-by-case basis. But ideally speaking, for a decision tree construction, since the tree is not built on a metric of distance, okay, we are not trying to measure distance. So normalization not normalizing doesn't affect the great extent. Okay. when the metric used for your classification is based on a distance, like a Euclidean distance you are trying to measure. If you are not normalizing the data, a higher range will unduly influence your distance calculation. That is why normalization is very critical if you are trying to arrive at a balanced classifier. But in a tree, not so much. Second, what all ML algorithms are available for addressing non-linear separate class levels? Oh, okay. Depends. For example, SVM is one classifier which does a very good job in terms of if the class boundaries are nonlinear. But beyond that, your nonlinear classifiers, like let's say neighborhood-based classifiers, do a fairly good job. Okay, but then again, you have this mechanism of NN versus KNN versus weighted and modified KNN and things of that nature. You have to be careful there, but they do a good job in terms of nonlinear class boundaries. And of course, deep learning techniques. I think you have already attended or you will attend another session on deep learning. Deep learning set of techniques, they do a fairly great job in terms of segregating classes which are nonlinear separability, that is class boundaries are nonlinear. Any other questions?
Any other question from the student side? I think no questions are there from the student side.
Great job. I will stop sharing now.
Yes, sir. Dr. Sandeep Parida, anything you want to say?
No, actually, yeah, thank you. I'd like to thank Professor Pitavaspati for the very wonderful session. I think it's a very good hands-on experience about decision tree, not only theoretical things, but the practical hands-on. Really, I think it's very valuable to visualize how it works really. And I have a quick announcement for like the second session. Actually, we'll mostly about the project explanation. So I have already mentioned that who want to present for which project, so they can email me so that we can provide. We are preparing a list, and accordingly we can proceed. And yeah, so now maybe I'll hand over to Session Chair to conclude this session. And before we start, they can also announce the next session.
So thank you, Pitavas sir. Such a nice presentation, and definitely it will be helpful for the students who wants to start the career in machine learning. So definitely this hands-on will be definitely helpful for them. So I think we should stop the session now, Sandeep.
Thank you very much.
So thank you so much. Anyone wants to say, want to take some help from the Pitavas sir, he or she can contact Pitavas sir for the projects or something, and they can contact me also.
And also,
let me also put it here. It's not restricted to only to this workshop, only to this seminar series. Beyond this, also, if you want to reach out, you can and take any help, please.
Yes, directly contact with our sir also. If anything is required, okay, any help is required, directly contact us. So, thank you, Masa. Thank you so much.
Thank you, and I think the next